All right. We recording me? Yeah, we appear to be. So what we're going to do today, and this will be a relatively shortish lecture, going to talk about power stuff, power considerations, and then confidence intervals around our effect sizes, okay? Effect sizes, just like any other estimate, is just a sample-based estimate of some population value. We're going to estimate effect sizes within precision, but there's some relevant math stuff that's going on with your confidence intervals that you'll want to make sure that you're accounting for. So, general overview here. But to go through and talk about and revisit the two types of error that we can make in our analyses, right? Again, if we take a look at our table here, if the null hypothesis is true, meaning that there's no difference, there's no association, anything going on, and I reject the null hypothesis in my test, what I've done is I've made a type 1 error. I've essentially claimed an effect when there is no effect to be had, okay? And this is the type of error that's really concerning and problematic within our traditional null hypothesis testing. This is, what determines our type 1 error? Lucas, when we're running our analysis, what determines our threshold for type 1 error? Our alpha level. This is what we're saying is our acceptable level of type 1 error, and this is what we're fighting against. And again, because no one wants, it's a selfish world. No one wants anybody claiming effects when there were no effects to be had, right? So this is what we're primarily concerned about, right? But we've also got a different type of error. We've got type 2 error, right? This is when when there is an effect, right? The null hypothesis is false, right? But I failed to detect it. If there is an effect and I fail to detect it, what I've done is I've said, I'm not saying there is no effect, I'm just saying we don't have evidence to claim an effect, but there is an effect to be had. That's why I've got some type 2 error. And we're less concerned with this in our tests. And arguments for this is actually problematic for a number of reasons, right? We have an inordinate concern with our type 1 errors. It's just that this is how our system is set up. Our system is set up, our test is set up to avoid type 1 errors. And so just because that's how the system is set up, that's the thing that we tend to focus on the most, right? We also have some historic difficulties with the calculation of type 2 error. What happens is we start to get into distributions that are different from our normal distribution, which creates some problems historically in the math. Less so today because we have computers, wonderful computing capacity makes this quite a bit easier, but still not 100% as easy as it should be or straightforward. But there's some stuff going on there, right? Other thing too, if we're thinking about type 1 error too much, it's going to make us as researchers feel really anxious and sad because these errors are all over the place, okay? And from a conceptual standpoint, if we're thinking about Cohen-Meal type of stuff, are type 1 errors real? Can I make a type 1 error according to Meal or Cohen? What do you think, Jenna?
No, because the null is technically never true.
Yeah, the null is never true, right? But I'm real worried about making a type 1 error. I'm worried about, I'm real concerned about unicorns, right? I did structure my whole life to avoid unicorns when it's probably not an actual real thing that I could encounter, right? And so really these type 2 errors are something that we should be concerned about, but we overlook this constantly, okay? Because what it does is starts to relate into power, okay? Conceptually, if we're thinking about power, right? Has everybody heard people talking about, does this study have enough power, things along these lines, right? People have heard this term. If we're thinking about this conceptually, thinking about power is the long-term probability of rejecting my null model given a particular effect size, alpha size, and sample size, okay? So if I were to replicate this experiment again and again and again and again and again, what's the probability of rejecting the null hypothesis? if the null hypothesis, or if the null hypothesis is false, right? And when we're going through, and so power is, you'll see it statistically notated as 1 minus beta, is how people identify power here. Most appropriately used for running our power calculations is going to be to look at the expected power of a planned study prior to data collection. So before I go through and I even start submitting my IRB, going through and saying, if I go through and run this study with this sample size, with this alpha level, and this assumed effect size, what's the power of this study likely to be? Okay. We can also use this, and this is maybe the more common, determine the sample needed to achieve adequate power, again, prior to data collection. Before I even get started with stuff, how many people do I need in order to adequately power this study, right? Think about this as a Vegas bet. Like, how good do my odds need to be before I'm willing to sit down at this table, right? I mean, it's a free country. I can run into something like, oh, odds are, like, my odds of winning are, probably most of us wouldn't be sort of comfortable just walking up to a roulette wheel betting double zeros every time, right? I'm not saying you're not gonna win occasionally, but it's just not a good bet, right? But we do this in research all the time, right? We say like, oh, I'm just gonna go through and collect 50 people and assume that that's gonna be good enough. That's a lot of time, effort, and energy spent for something that's almost certainly gonna come up null. Okay. Other thing that we need to be thinking about in terms of power is recognizing that power is not an exact science. We use, again, exact numbers, and we get sort of our fancy power calculations, things along these lines. This is horseshoes, it's not target shooting, okay? The goal is to see like, hey, I'm gonna run this study, is my power closer to 0.8 or 0.3, okay? Number of different reasons for this. In our science, power equal 0.8 is kind of our accepted, let's see, too much power, is our accepted standard for adequate power, okay? If I have less than 0.8, so the idea is that I have an unacceptable risk of type 2 error, right? If my power is 0.5, I'm basically saying, if I run this study, it's a coin flip on whether or not I'm going to detect this effect or not, right? But we can also have, if we have power that's too much, right? If I got a power of 0.80, make an argument that I have an inefficient use of resources, particularly depending on what I'm doing, right? If I'm paying participants on Prolific or MTurk or something like that, and I need 100 people to go through and reasonably power my study, and I collect 500 people, I've just wasted a lot of money to do that, right? From an ethics standpoint, right? If I'm working through something that's pretty onerous, maybe dangerous or risky, right? And I only need 50 people to determine the reasonable power of the thing that I'm doing, but I want to go through and collect 150, that means I put 100 extra people through potential risk when they didn't need to do it, because I didn't need that much, right? Kyle DeYoung gave a talk, he was like talking about some folks that had done some rat research, and it was small sample, it was like 8 rats or something along those lines, right? He's like, oh, do you have problems with sort of that small sample of rats? He's like, yeah, like people don't like it, but also if you're doing rat research, anybody done neuroscience like rat lab stuff before? It doesn't turn out well for the rats at the end, right? And like you think about, so like, okay, so we're doing this and sort of setting this up ethically, but how many rats are we gonna sacrifice to go through and do this, right? If I can do it with 8 and I don't have to slaughter 20, like maybe not gonna go through and do that, right? So there's some ethical things to think about here. But then we also have, for overpowered studies, if we're not being careful, the potential for unwarranted conclusions. If I have a data set of 5,000 observations, probably anything in there is going to be highly statistically significant, right? That doesn't mean it's meaningful or practical. Probably all that means is it's just verifying that I have a ridiculously large sample, right? But if I'm not thinking carefully about that, I can start to draw conclusions about you know, how reliable or how massive or how important this relation is, when in fact it's not. It's the only reason it's coming up is because it's not exactly 0, okay? So again, like thinking about if I get a national, a large national sample, like 8,000 people, probably any two variables that I'm look at are going to be highly correlated, or be associated with a very small p-value, which I can say is highly statistically significant. Well, it just means it's not exactly 0, right? It might be a correlation of 0.08, right? So we need to be careful in thinking about things, okay? Questions about power and sort of some considerations about sort of how we should be thinking about this and setting this up. Okay? And so again, if we need to think about the things that we need to sort of calculate power, we need to have alpha. That's fine. That's sort of kind of a given, right? Given our science. Our sample size, that's something we can kind of play around with. But the big thing is here's this effect size. What's the effect size I'm looking for, right? And there's a lot of reasons why getting that effect size can start to become really difficult. So if we want to think about empirically what's going on with these power calculations, okay? If we take, so let's say this study, an older study on stereotype threat, okay? And what they're looking at is this idea of stereotype threat. Folks who are social people sort of recognize this. The idea that if I perform a task when stereotypes about my group are made salient, what ends up happening is it impacts my performance, right? And so here, what researchers have done is they've pulled in a bunch of white men to take this math test or whatever the cover story is, right? But what they do is they have some subset of men go through and can just complete the math test task and just go ahead and let them do it. But then they're going to have a threat group, right? And this threat group, they're saying before they go through and let people go through the bag, oh, here, go through and do this. By the way, Asian students generally perform better on this test than you will, right? And so again, the idea is this, it's sort of priming these, and what we would expect is low performance on this test because this stereotype has been made active, okay? So we go through and we do it. Let's say we have 20 people in the control group, 20 people in the threat group, and the mean performance for the control group is 9.6, my threat group is 6.6, and my standard deviation, okay? So people understand kind of like sort of the setup for the experiment, what they've got going on. So if I were to calculate power, right, to go through and I wanted to say, how do I go through and sort of determine the power of this experiment here? What I would do is first go through and say, I've got a population of scores, like a bigger population. This represents my control group, right? And the population mean is 9.6, the standard deviation 3.2, okay? In the population, hypothetically. What I'm going to do is I'm going to go through and select 20 observations from that population of scores, okay? Again, so it's sort of a distribution. Not everybody has the same value here, but I go through and I draw 20 people from this hypothetical distribution. And then I go through and I select 20 observations from a population of scores having a mean of 6.6 and a standard deviation of 3. Again, this other basket, different distribution. I go through and pull 20 observations from this. Okay. People following me? And so then what I'm going to do is from this sample that I pulled and this sample that I pulled, I'm going to go through, I'm going to calculate my test statistic for the difference in means, going to go through and record this, okay? So what I've essentially done is I've gone through and pulled a sample from a population with these characteristics, pulled a sample of 20 from a population with these characteristics, then I'm just going to run a t-test and see what the difference is, right? And then I'm going to do this 10,000 more times, okay? And if I do this and plot out the distribution of t-statistics, right, for these 10,000 replications, what I would do is I would look at the t-values here, and I would say, here's the distribution of t-values for this 10,000 replications, okay? What is the critical t for an independent sample t-test with 38 degrees of freedom? Because that's the t-test we're running here, right? We got 20/20, independent sample t-test is degrees of freedom is total sample minus 2, so we got 38 degrees of freedom. My critical t is 2.047. And what I would do is I would look in this distribution, find 2.4 or 2.024, and then look at like how many of these tests found that and found that or higher, and then how many did not. Okay. So my mean value here is 3.12. That's what you get out of there. Okay. And so again, the question is, in this distribution, how many t-values are at or beyond 2.024? And if we actually look at this, we get 86% of those t-values falling beyond this distribution, or falling at my critical value or above. Okay? So again, thinking about power as the long-term probability of rejecting the null hypothesis. Okay? In this empirical example, what we're doing is we're saying that Aronson's data is perfect, for this example, for the purpose of argument, saying that this is perfectly capturing the actual population means, right? But sometimes, if this is the population mean, standard deviation, population mean, standard deviation, sometimes we're going to get samples where my threat group is performing better than my control group. Not often, but sometimes, right? And sometimes I'm going to get samples where these two are actually pretty close, right? But of these, how many of these test statistics are going to tell me, yep, allow me to reject the null hypothesis, right? So what is, if this is, what is the value of my power in this example? Do you know?
So the 86%.
Yeah, it's 0.86, right? My power would be 0.86, which is saying 86% of the time, I'm going to find it, if these are the actual population values, if this is what we're looking for, 86% of the time, my test with a total sample of 40 is going to allow me to reject the null hypotheses. But it's also saying that 14% of the time I'm going to miss, right? Just in the way this distribution is set up. People see this as sort of this idea of a long-term probability and how this kind of works out. Just to make this more clear, if I'm going through and I'm saying I have a population with mean equal to 9.64, standard deviation 3.17, and I've got my other population where my mean is equal to 6.58, standard deviation here is 3.03, right? If I take 20 scores out of this, 20 scores out of this, and run a t-test and see what I get, then I do it again. 20 new scores out of here, 20 new scores out of here. Do it again, do it again, do it again, do it again. Long-term probability, over the long term, I'm going to get a distribution of those t-statistics. My power is telling me, assuming that these are the true population values, how many of those t-test statistics will I expect to allow me to reject the null hypothesis, right? Because sometimes I'm going to get stuff that's way down. I get a sample where my mean's way down here and up here, and I'm going to have a miss, right? I'm going to make a wrong decision here, or fail to identify. But over the long term, 86 of those percent of those are going to give me the right decision. Questions about this? All right. Another way we can think about power conceptually, okay? And this is just like, how do we make this sense of this in our head? You can think about power as representing overlapping distributions, okay?